Layered communication models exist to explain how data moves from one system to another and to give engineers a shared way to reason about where controls, failures, and threats apply.
Without layers, network discussions quickly become confused because people talk past one another while referring to different parts of the same process. Layered models break communication into conceptual stages so you can isolate responsibility, understand dependencies, and place security mechanisms deliberately. This approach is especially valuable in security because many controls only function at specific layers and cannot compensate for weaknesses elsewhere.
When you understand layered models, you gain a mental map that helps you design, defend, and troubleshoot networks with far greater precision.
Before we continue, a quick note. This audio course is a companion to the CISS books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. The Open Systems Interconnection model separates communication into distinct layers that range from physical signal transmission up to application-level interaction. At the lowest layers, the model concerns itself with how bits move across wires or wireless signals and how frames are formed and transmitted. As you move upward, the focus shifts to logical addressing, routing, transport reliability, session behavior, and finally, application semantics. Each layer provides services to the layer above it while relying on the layer below it, creating a structured dependency chain. Even though real-world protocols do not always align perfectly with this model, the conceptual separation remains useful. It allows engineers to discuss problems and controls without conflating electrical issues, routing issues, and application behavior.
The Transmission Control Protocol/Internet Protocol model, often abbreviated as TCP/IP on first mention, groups communication functions into fewer layers that reflect how the modern Internet actually operates.
Instead of 7 layers, it typically describes link, internet, transport, and application layers. The link layer covers local network access. The internet layer handles logical addressing and routing. The transport layer manages end-to-end communication characteristics, and the application layer encompasses everything from message formats to authentication. This model is more pragmatic and maps closely to real protocols in use today. While it is less granular than the Open Systems Interconnection model, it is often easier to apply directly when diagnosing real network behavior. Encapsulation is the process that allows layered communication to work by wrapping data with headers as it moves down the stack. An application creates data, which is then wrapped with transport information, then network addressing, and finally link-level framing before transmission. Each layer adds its own header containing information needed to deliver the data to the next hop or the final destination. On the receiving side, the process is reversed as each layer removes its header and passes the remaining payload upward. Encapsulation allows each layer to operate independently because it does not need to understand the internal details of the layers above or below. This abstraction is what makes layered design scalable and flexible.
Addressing works differently at different layers, and understanding those differences is critical for both security and troubleshooting. At the link layer, devices use media access control addresses to deliver frames within a local network segment. At the network layer, Internet Protocol addresses identify logical locations across interconnected networks. At the transport layer, port numbers identify specific services or processes on a host. Each addressing scheme serves a different purpose and has a different scope of visibility. Confusing these layers often leads to incorrect assumptions about reachability, identity, or trust. Security controls must respect these distinctions to be effective. Routing is primarily a function of the network layer, where packets are moved between networks based on logical addressing. Routers examine destination addresses and forward packets along paths determined by routing tables and protocols. Routing decisions influence performance, availability, and security because they determine which networks traffic traverses. Misrouting can lead to outages, interception, or exposure to untrusted paths. From a security standpoint, routing is also where segmentation is enforced at scale, because controlling routes controls which systems can even attempt to communicate. Understanding routing behavior is essential for predicting how traffic flows and where to place controls. Transport protocols sit above routing and manage characteristics such as reliability, ordering, and flow control. Some transport protocols provide guaranteed delivery and ordered streams, while others favor speed and low overhead at the cost of reliability. These choices affect how applications behave under loss, congestion, and attack conditions. Transport behavior also influences security controls, such as rate limiting, connection tracking, and session timeouts. Because transport protocols operate end-to-end, they can be affected by conditions anywhere along the path. Security architects must account for these behaviors when designing defenses against denial of service and resource exhaustion.
Session behavior is not always a distinct protocol layer, but it is a useful concept for understanding how connections are established, maintained, and terminated.
Session management includes connection setup, teardown, and state tracking, which are all relevant to authentication and authorization decisions.
Many attacks target session handling by hijacking identifiers, replaying messages, or exploiting weak termination logic.
Understanding where session state is created and enforced helps clarify which controls are responsible for maintaining continuity and trust. Poor session handling often leads to subtle vulnerabilities that are difficult to diagnose without layered thinking. Application protocols define the structure and meaning of messages exchanged between systems. This includes data formats, commands, authentication methods, and error handling behavior. Application protocols are where business logic lives, which makes them a frequent target for attackers seeking to bypass authorization or manipulate outcomes. Security controls at this layer include authentication, authorization, input validation, and content inspection. These controls cannot be replaced by lower-layer mechanisms because lower layers do not understand application semantics. When application protocols are poorly designed or inconsistently implemented, no amount of network filtering can fully compensate. Threats often align naturally with specific layers, which is why layered models are useful for threat analysis. Spoofing attacks often exploit weaknesses in addressing layers, while routing manipulation targets network layer assumptions. Transport layer attacks may abuse connection management or resource allocation. Application layer attacks focus on logic, data handling, and trust decisions. Recognizing where a threat operates helps determine which controls are relevant and which are ineffective. This alignment prevents wasted effort and improves the precision of defensive design.
Firewalls and proxies illustrate how controls map to layers in practice.
Traditional firewalls often filter traffic based on Internet protocol addresses and ports, which places them primarily at the network and transport layers.
Proxies operate at the application layer, allowing them to inspect content, enforce authentication, and apply granular policy decisions.
Each approach has strengths and limitations based on the layer it operates at.
Understanding these differences helps avoid unrealistic expectations about what a given control can achieve. Effective architectures often combine controls at multiple layers rather than relying on a single mechanism.
Encryption can be applied at multiple layers, and where it is applied changes both protection and visibility. Encryption at the transport or application layer protects data end-to-end, but limits the ability of intermediate devices to inspect content. Encryption at lower layers may protect traffic on specific links while still allowing inspection elsewhere. These choices affect monitoring, troubleshooting, and policy enforcement. Architects must balance confidentiality needs with operational requirements for visibility and control. Layered models help clarify these trade-offs by making explicit which layers can still observe meaningful information. Troubleshooting benefits greatly from layered thinking because it allows engineers to isolate where a failure occurs rather than guessing broadly. If a system cannot communicate, you can ask whether the issue is physical connectivity, addressing, routing, transport behavior, or application logic. This structured approach reduces time to resolution and avoids unnecessary changes that introduce new problems. In security incidents, layered troubleshooting helps distinguish between network-level disruption and application-level abuse. Clear mental separation of layers leads to faster, more accurate diagnosis.
Layered models provide a shared language for network security decisions by giving teams a common framework to describe communication, controls, and failures. The Open Systems Interconnection model offers conceptual clarity, while the Transmission Control Protocol/Internet Protocol model aligns closely with real-world implementations. Encapsulation, addressing, routing, and transport behavior explain how data moves and where it can be influenced. Application protocols and session handling show where identity and logic must be enforced.
By grounding security discussions in layered models, architects and operators can design controls that align with reality rather than assumptions.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.